Surface plasmons were first discovered in 1907 when Jonas Zenneck analyzed the propagation of electromagnetic wave over an extended metal surface. Here, we will focus on the tremendous potential of surface plasmon or photonic circuitry and discuss the issues and challenges the scientists in the field are facing. So, why do we need surface plasmon circuitry? The simple reason behind it is the mismatch between the large-scale integrated photonics and small-scale integrated electronics. Modern-day electronic circuits have dimensions of tens of nanometers, and the conventional photonic device size is about the order of lambda by 2 or 500 nanometer. Fortunately, signals in plasmonic waveguide can have transverse dimension smaller than 100 nanometer. Plasmonic device can be 100 times smaller and 1000 times faster than current photonic devices.
To communicate, we need a plasmonic waveguide. Plasmonic waveguide can be of three types. Metal insulator interface. The simplest plasmonic waveguide with a single interface between a metal and a dielectric supporting a bounded SPP. Insulator metal insulator waveguide offers longest propagation length and is bounded by semi-infinite dielectrics supporting a bounded SPP. Metal insulator metal waveguide allows for very small transverse dimension. It consists of dielectric slab bound by semi-infinite metals supporting a symmetric and bound SPP. The imaginary part of the complex wave vector along the metal dielectric interface determines the propagation length because it relates to the damping inside the metal. The fact that the length decreases as the SP becomes more confined reveals an important fact in the context of SP circuitry, that the maximum propagation length and the maximum field confinement lie on opposite ends of the SP dispersion curve. To increase the confinement and propagation length, different strategies have been proposed and tested. One of them uses thin metal strips embedded inside a dielectric to guide the SPs, as metal planes whose thickness is order of the skin depth can sustain so-called long-range SPs. But the long-range surface plasmons are diffraction limited, and significant radiation losses can occur in geometries that contain sharp bends and high curvatures.
Two general schemes are used to couple light to the SPs. In the first, the coupling is achieved by matching their momenta. In a different approach, the coupling relies on matching field distribution across the end face of a metal dielectric interface. This is known as end-fire coupling. This method is efficient and allows a large range of frequencies that can be coupled for a given geometry. Ultimately, practical photonic circuits might use a combination of plasmonic and dielectric components, taking advantage of the best performance available.